I want to talk about what physics can tell us about our own existence. Where do we come from? Where do we go to? How much do we know and how much can we know? And I've summarized this under the title Existential Physics, which is also the title of my new book, which will be coming out in August. The entire story of my new book started at this event in 2018. What happened was that someone came to pick us up in Hereford and combined several of us in a car. So I was stuck in a car with some other people who I didn't know for half an hour. And there was a young man sitting next to me, and I can't remember his name, but he said he's a DJ of kind, and he'd be playing music at an evening event, and asked me what I'm doing. And I said, well, I'm a physicist. And he said, oh, that's interesting. And he told me he talked to a shaman who told him that his grandmother was still alive because of quantum mechanics. And at this point, I would normally have excused myself, but it wasn't an option. And so I thought about it for a little bit, and maybe surprisingly came to the conclusion it's not completely wrong. And so normally I wouldn't have said, I wouldn't have said anything about it, but this question made me realize that physics does say something about us, just because everything obeys the laws of nature. Everything lives in space and time, and we're all made of the same matter. And that led me to realize that physics says something about those really big questions, and it's something that we don't normally talk about for the same reason I wouldn't normally have talked about, because we're not comfortable talking about life and death and consciousness. So the idea was born that I would write a book about those big questions and how much physics can tell us about it. And the message that I wanted to get across is that physics isn't just about balls rolling down inclined planes and Ohm's law and all that kind of stuff which you learn at school. It's about so much more than this. Well, it doesn't tell us what life and consciousness is, but it does tell us what rules life and consciousness has to work with. And that does tell us something. So this was the title I originally chose. It was also a nod, of course, to this song from Roxy Music, which maybe some of you may remember, which I've always found a little bit depressing, but ultimately I thought it was a song about determinism. While the sea on the tide has no way of turning, more than this, there's nothing. And I wanted to say, it's true that everything's made of particles, but there's so much more than this to physics. There's so much more that we can learn from the laws of physics. I think it's kind of missing the point. Yes, we're all made of particles, but look at all the fascinating things that these particles can do. There's some amazing stuff that comes out of combining all those particles, like society is culture. There are living beings, consciousness, and those living beings have figured out how to discover the laws of nature that govern their behavior. So I think that's all pretty amazing, and that's a story that deserves to be told. My editor didn't like the title more than this. He thought we have to get the word physics into the title. So I had to come up with something. What I came up with is that existential physics is about those aspects of physics that concern human existence. Where do we come from? That concerns the beginning of the universe. What are we made of? That's the structure of matter. What can we know? Are there limits to knowledge that come from the structure of those fundamental laws? What can change? And maybe some others. So in this talk, I'm not going to go through all the questions in my book, because I want to leave you a reason to buy the book, of course. But I have picked some. So when I wrote this book, I noticed that I was constantly using the phrase, for all we currently know. For all we currently know this, for all we currently know this. So in the end, I just decided to put this into the preface, and I wrote, everything I say in this book should come with the little asterisk, this is for all we currently know. And the same is the case for what I say in my talk, unless I explicitly say it's a speculation. It's just for all we currently know. And as it goes in science, it might always be that there'll be more evidence coming in at some point, and we'll understand a little bit more, and the story would change. Okay, so I start with the question, does the past still exist? Which is basically, I think, the question that this young man asked me 4 years ago. So I think the answer is yes. So why do I think this? Well, this is really an insight that came from Albert Einstein. So Albert Einstein came up with this theory of special relativity, which is based on the idea that time is a dimension. So time used to be some kind of universal parameter. So we all shared the same moment, the same passage of time. There was a universal now that we could all agree on. This was in the days before Einstein. And then Minkowski figured out that actually this idea that time is a parameter, a universal parameter, doesn't really make a lot of sense if you look at Maxwell's equations of electrodynamics. So he figured out that those equations have a particular type of symmetry. So it's kind of similar to when you take a ball and you rotate one direction of space into another and the ball doesn't change. And Maxwell's equations also have a symmetry if you rotate one dimension of space into time. And Minkowski said there's an easy way to make sense of this. We just combine space with time, and then we can rotate in space-time. And that explains why Maxwell's equations have this structure. It's got nothing to do with electrodynamics. It comes from the structure of space-time. But what does it mean? Well, it took Albert Einstein to figure out what this means. And his theory of special relativity is, roughly speaking, based on these three starting points. Time is a dimension, and we live in this four-dimensional space-time, 3 dimensions of space, 1 of time. The speed of light is finite, and the speed of light in vacuum is the same for all observers. And I should also have added here probably, but you know this already, nothing can move faster than the speed of light. And all observers' viewpoints are equally valid. Now, it's kind of hard to draw 4 dimensions, but I can at least draw 2. So we have only 1 dimension of space, and we have 1 dimension of time. This is called a space-time diagram. And in a space-time diagram, if you just sit there on your chair, you just make a straight line up. So you're not moving in space, you're just going forward in time. If you move at constant velocity, you make a line that's tilted at an angle. You can't go faster than the speed of light, so the speed of light is normally conventionally drawn at a 45-degree angle. So those gray shaded area, you can't enter those. But the general curve is like some curvy line that at any point has to stay below the speed of light angle. So this looks pretty innocent, and all by itself doesn't really mean anything. But let's look at what the consequences are of those other assumptions that Einstein started with. There's the speed of light is finite. And that sounds pretty unremarkable. But it has some interesting consequences. So when you see and hear me speak, you see and hear what happened a fraction of a second in the past. So if I ask you, am I here now? How do you know? By the time you hear those words, I could already have done something else. Maybe I just disappeared. Or you may say, well, come on, this is insane. Of course you are here now. But how do you even know what now is? What are we even talking about? Now, you could say, well, just look at this diagram. Clearly, this horizontal line that we can draw, this is now. Okay, we can just all agree on this and move on with our lives. But just drawing a line in a diagram isn't physics, right? We have to come up with an operational definition. How can we construct this moment in time? How could we measure it? And Einstein tried exactly this with what he called a laser clock. It works like this. So what you want to do is you want to come up with a definition of now at a place which is not also here. So you might want to know if I am here now. So Einstein said you can do the following. You place yourself between 2 mirrors and you send a laser beam, one to each side. send them out at the same time, wait until they come back. If they don't come back at the same time, you know you're not exactly in the middle between the mirrors, because the speed of light is constant. It's always the same. So you move around until the photons come back at the same time. Then you know you're in the middle. And once you have done this, you can tell that exactly in the middle between sending out the photon and them coming back, the photons must have hit the mirrors. So you could stand in the middle between the mirrors, look at your clock and say, now the photons hit the mirrors. So now you have a way to tell what happens now at a place where you are not, which is at the mirrors. Okay, great. So we've done it. We seem to have defined a notion of simultaneity with this laser clock. Well, here's the problem. Suppose you have a friend, let's call her Sue, who is flying by in a spaceship or what have you, and she's doing exactly the same thing. So she has two mirrors, one left to her, one right to her. She sends out her photons, positions herself until the photons come back at the same time, and then from this she defines her notion of simultaneity. Now you would say, this is obviously wrong, because these photons do not meet the mirrors at the same time. It takes longer for the photon to hit the mirror in the direction where she's going, so which would be this direction, so pointed in the wrong direction. So the mirror is running away from the photon, so it takes longer to get there, whereas the photon that goes into the other direction is running into the mirror, so it gets there earlier. So for you, those two events do not happen at the same time. Okay, so she seems to have constructed a notion of simultaneity, or a notion of now, that from your perspective just looks wrong. And to make things even more confusing, if you ask her what's going on, then she would say, well, you're the one making a mistake, because from her perspective, you're the one who's moving, and your mirrors are running away from the photons. So this is all pretty weird. So what does it mean? Well, it means that in general relativity, in special relativity, there is no way to construct a notion of simultaneity that does not depend on the observer. So this entire notion of now is observer dependent, the way that physicists phrase it. So this is pretty mind-boggling already. It takes some time to wrap your head around. But it actually gets worse than this in special relativity, because there are some really odd consequences from this. So what this example with the laser clock shows you is that any two events that are not in causal contact are simultaneous for some observers. So first I should explain what does it mean for them not to be in causal contact. It means you cannot send any signal from one event to the other. In a space-time diagram, this just means if you draw a straight line from one event to the other, then the angle of the line with the horizontal is less than 45 degrees, because that's how we have defined the speed of light. So suppose you have some event that is not in causal contact with your birth. So this little star is supposed to be the event where you were born, and there is a supernova explosion far, far away in a distant galaxy which is not in causal contact with the event of your birth. Well, there is always some observer for whom those two events will be simultaneous. They would say they happen now, because you can put the observer in the middle, and then you just have to adjust the velocity of the observer until the photons, the imaginary photons, you could say, this is all theoretical physics, right, would come back from the mirrors that would go exactly through those two events. And now the next problem is, if you have two events that are in causal contact, say your birth and your death, then you can always find some event which is not in causal contact with both. For example, again, this supernova, and now there are two observers for whom both pairs of events are simultaneous. So what this means is, if you are willing to accept that anything exists now which is not also here. And you believe that Einstein was right with his theory of special relativity, you're forced to accept that everything that some observer thinks exists now is equally real. And this ultimately means that everything which happens somewhere in space-time is equally real as the present moment. Okay, so that is a little bit hard to swallow. Maybe what's even more surprising is that this is a completely standard argument which we learn as undergrad students. And the first time we hear about it, everyone sits there like, what, really? And then you walk around like for 2 days thinking this can't possibly be right. But that's just the way it comes out in special relativity. It even has a name. It's called the block universe, because the universe just sits there. It's there already. We just haven't seen the future, basically. Now, there is a little asterisk that I have to make here, because you've probably all heard of quantum mechanics. So quantum mechanics is a little bit more complicated than this, but to make a long story short, quantum mechanics is still compatible with special relativity. So the key argument that I just made doesn't really change. The major difference in quantum mechanics is that it has an indeterministic element. So you could say that the future isn't actually fixed because there's some random chance in the time evolution, but the arguments would still go through for the past, which is where I wrote, the past still exists, about the future, well, I don't know. Okay, so does the past still exist? For all we currently know, yes. That just comes out of Einstein's theories. We get to the next question, is actually quite related to this one. Can information be destroyed? And the answer to this is, it depends. And I go on to explain exactly what it depends on. So if you think about what you learned about physics in school, maybe Newton's law, you know, you have an arrow and you know the initial position and the initial velocity of the arrow, then you can calculate exactly where the arrow will land. This is an example of natural law that we're all familiar with. But actually all the natural laws that we use in the foundations of physics work exactly the same way. We have some initial state, then we have an equation which is called an evolution law, and from this we calculate a final state. We can also do this backwards. So if you know where the arrow landed and what the velocity was by which it landed, you can calculate where it came from. So those time evolutions that we have, they're all time reversible, at least in principle. So when I say time reversible, I just mean you can use this law forward and backwards. Of course, in practice, a lot of things are not time reversible just because they're really, really difficult. Like if you're mixing batter, for example, it becomes so difficult so quickly that you cannot, in practice, ever actually figure out what the initial state was from the final state. But in principle, you know, again, this is theoretical physics, you could, if you knew exactly where all the single molecules are located in your bowl, you could figure out what the initial state was. Okay, so I asked the question like, can information be destroyed? Well, we have to talk about what do we mean by information. What I mean by information here is just all the data that you need to specify the initial state. And what happens in all those evolution laws is that the information is reconfigured, but it can never get destroyed, because in principle you could always take the final state and apply your evolution law and figure out exactly how it started. This is another reason why the past still exists in some way. You just rearrange things in the universe, you never actually destroy them. So yeah, so I said this is all fundamental laws, except there are two things which don't fit in this pattern. So in quantum mechanics, we do have an evolution law which is time reversible. That's called the Schrödinger equation, and we can use this forwards and backwards. But this isn't the only thing that's going on in quantum mechanics. In quantum mechanics, we have a second ingredient to what happens in the universe, which is the measurement update. So quantum mechanics, everything is described by what's called a wave function. So there's a wave function for everything, for electrons, for atoms and molecules, but also for you and I, and in principle for the entire universe. So we describe everything by this thing that's called the wave function, but the wave function itself is not observable. It's just a device to calculate probabilities. And so what happens when you actually make a measurement on a single particle, suppose you have the left probability distribution for an electron or something. The moment you measure the electron, you know where it is. So suddenly, you know with 100% probability where the electron is, which means you have to update your wave function the moment you make a measurement. Now, the problem with this is that once you have made the measurement, you no longer know what the wave function is that it came from. Could have been anything. You know, maybe the 100% were peaked with 60%, or maybe it was just 20% and you just got lucky. There's no way of telling. So this measurement process is irreversible. You cannot tell from the final state what the initial state was. This is one reason why information could actually get destroyed. So you can't figure out what the initial state was. Measurements in quantum mechanics do destroy information if you think that the theory, that the way that we currently use it, is actually fundamentally correct. And there are some reasons to doubt this. One of the major clues that maybe quantum mechanics isn't the final story is that it requires you to talk about detectors to begin with. If quantum mechanics was really a theory for the fundamental constituents of matter, then it should explain what a detector does. You should be able to calculate it. Instead, quantum mechanics has to assume that you know what a detector is. And that's certainly true to some extent in practice. You know, we know a detector when we see it, but the theory doesn't explain it. And so I think this is the clue that quantum mechanics isn't fundamentally the right thing. And there's also the question, like, if we have a wave function for the entire universe, well, who measures this? There's no one to measure it. Those, I think, are reasons to be kind of skeptical that the measurement update is actually the right description of the physical process. But as I said, I'd warn you if this is speculation. This is just speculation. Okay, so the other process which might actually destroy information is black hole evaporation. So normally the way that black holes are introduced is if you throw something in, it can't come out. So it's forever hidden behind the horizon. So you could say, well, if I take a book and I throw it into a black hole, then it's gone. But that's not necessarily a problem, because just because you can't access some information doesn't mean it's been destroyed. You know, if I take a book and I lock it into a chest or something, you can also no longer access it, but you wouldn't say that the information has been destroyed. So you could say maybe the same is going on with black holes. But then in the 1970s, Stephen Hawking came and said, well, the black holes don't sit there forever, but they evaporate. They emit what's now called Hawking radiation, which is basically completely random radiation, contains all the particles that we know of in different fractions. And the important thing is that this radiation contains no information other than the mass of the black hole, but very few bits, so to speak. And it carries away energy from the black hole, and the entire energy is conserved. So what happens is that the black hole shrinks, and it radiates and it shrinks, and eventually it's entirely gone. The only thing that's left is a lot of this Hawking radiation, which doesn't contain any information. So if you've thrown in your book into the black hole, the information really gets destroyed. It's a process that's not reversible. And there are lots of problems with this. One is that if you just take this process of black hole evaporation, it's inconsistent with quantum mechanics even before you make a measurement. Because as I told you, the time evolution in quantum mechanics, the Schrödinger equation is reversible. Yet the time evolution of black hole evaporation is inconsistent with this reversibility. So something doesn't match up. And then after this, maybe you make a measurement, but the problem occurs already before this. This is the reason why most physicists currently believe that something is missing in Hawking's calculation. For example, this calculation doesn't contain anything about the quantum properties of space and time itself. That's because we don't have a theory for the quantum properties of space and time. That's normally called quantum gravity, so that's not in the calculation. That may be a reason why the result isn't correct. There are lots of other solutions physicists have put forward that I don't want to go through, but that'll be another 2 hours or something. But the bottom line is that we don't know. We believe there's something wrong with this calculation. Hawking himself actually changed his mind. He originally thought information is actually destroyed in black hole evaporation, but later in his life changed his mind and thought that actually it comes out at some point. But we can't experimentally test it. The reason is that the black holes that we actually know exist out there in the universe, they're very massive, and the Hawking temperature is inversely proportional to the mass. So the heavier the black hole, the smaller the temperature. And the temperature of all those black holes is so small that we can't measure it. It takes them hundreds of billions of years to evaporate. So we can't experimentally test it, and the bottom line is we don't know. So the answer to the question, can information get destroyed, depends on what you believe happens in a measurement in quantum mechanics and in black hole evaporation. Personally, I think the answer is no. I think really fundamentally those two processes are time reversible. So then let's talk about the question, how did the universe begin? Where do we all come from? And if you read any popular science news about physics at all, you've probably heard countless different stories about this. My brief answer is we don't know. And I'll try to explain why I say this. So the way that modern cosmology works is that we use Einstein's equations for general relativity. So those equations, to make a long story short, they explain how space-time behaves in reaction to the distribution of matter. In particular, this theory tells us that the universe expands. You've probably all heard of this. We've also figured out that not only does it expand, the expansion actually gets faster. And the rate of expansion is determined by the amount of matter and energy in the universe. And so the other way around, you can measure the expansion, and you can infer what has to be in the universe. And this theory makes a lot of predictions. For example, the formation of structures, their pace and the distribution, the cosmic microwave background and the properties of the cosmic microwave background, the abundances of the lighter atoms, the redshift of distant galaxies, etc., and etc. So this theory, which we have for the universe from Einstein's theory of general relativity, is pretty good, and physicists are quite happy with it. It has a little problem, which is if you take those equations and you extrapolate them back in time, well, as I just said, the universe currently expands, so if you go back in time, then everything gets closer together and the density of matter increases and increases, and eventually it'll be infinitely large. That's a singularity. It's not only the energy density that becomes infinitely large, but also the curvature of space. And it happens at a finite time, at about 13.7 billion years before now. And this is called the Big Bang. Actually, I should probably add that physicists, pretty much no one believes that there was actually a singularity at the Big Bang, but it's probably just a sign that the equations break down at some point. So physicists use the word Big Bang to refer to whatever it'll be that replaces the singularity. But now remember how natural laws work. As I told you earlier, you have an initial state, you have an evolution law, and you get to a final state. Now, this brings up the following problem. Suppose you make a measurement for your final state, as we do in cosmology. So we have a measurement right now. We have an idea how the universe looks right now. Then we have an evolution law, and the evolution law gives us an initial state. So we work back in time. This is exactly what we do if we want to explain what happened in the early universe. Well, the issue is that you can take any evolution law, and it'll give you an initial state. And then if you take this initial state and you apply the evolution law to it, that'll correctly give you what we observe today. So how do we ever know which law is the right law if there's always some initial state that you can construct from our observations? Well, the answer is that this evolution law, together with the initial state, has to actually explain what we observe. It has to be a simple story to some extent. It's basically Occam's razor. So if you think about what I told you earlier, all the things that modern cosmology explains, like the cosmic microwave background and the structures and so on, those all come out of a simple initial state. And the theory actually tells you how those different things belong together, like how the formation of structures and distribution of galaxies and their correlations and so on hang together with the properties of the cosmic microwave background. This doesn't work for any initial state. Generically, you'd have to put a lot of information in the initial state so it wouldn't be simple anymore. So what this tells us is that the key justification for using a theory for the evolution of the universe is that it has to be simple. It has to be a simple explanation for the observations that we have today. So what physicists have done to replace this problem with the singularity of the Big Bang is that they have replaced part of this evolution law early in the universe. So you take the normal Big Bang theory up to a certain moment in time, depends on exactly how you want to do it, then you add a different evolution law and you use this evolution law to go back further in time. This gives you a different initial state and it can get rid of the singularity and it can have all kinds of other consequences. So you change the equations and then, as I said, you'd always get an initial state that then fits together with those equations to give you what we actually observe. And there are lots of different theories that have come out of this. For example, there may not have been a Big Bang, there might have been a big bounce. So there was an earlier universe which contracted and then it didn't go to a singularity, but it just shrunk to a very small size and then it began to expand again. There could be cycles. Roger Penrose, for example, has a model for a cyclic cosmology. There's an idea that's called asymptotic silence, where basically the early universe was just sitting there for a really, really long time not doing anything, and then suddenly it decided it'd expand. This also gets rid of the singularity. There's the no boundary proposal from Hartley Hawking, where you basically get rid of time entirely, so there's only space, 4 dimensions of space. Some think maybe there was neither space nor time, there was just a pre-geometric phase, maybe some kind of a big network that had to condense into a form where it would give rise to something that approximates space-time to a very good precision, 5-dimensional black holes, string gases, and so on and so forth. It's a really long list. But those ideas all work the same way. You change the evolution law somewhere back in time, and then you have a different initial state. Now, what's the problem with this? Well, as I said, a good scientific explanation must be simpler than the observation it's trying to explain. And the problem with all those theories for the early universe is that they make a simple story more difficult. But a good scientific explanation should be as simple as possible, and you shouldn't add any unnecessary assumptions, no matter how much you would like there to be a cyclic universe. It's as as Laplace put it, I had no use for this hypothesis. We also don't really have a use for the hypothesis of an infinite number of cycles. It's absolutely unnecessary to explain what we currently observe. And so this is why I say all those stories, they're basically tales, they're creation myths written in the language of mathematics. They're mostly not wrong in the sense that all those physicists, I mean, it's not like they're dumb, right? They make a big effort to get a theory that actually agrees with observations. Of course, I mean, there are some people who argue that this or that idea doesn't actually fit with observations, but that's a little bit beside the point. Mostly they're trying to actually get the observations out right. So they're not wrong, but we can't tell that they're right because they just add this unnecessary structure at a time where we don't actually have any data. So basically, you can believe whichever one you like, and my friend and colleague Tim Palmer has dubbed this ascientific. It's not that it's non-scientific, it's just that science can't actually tell you which is the right idea. Will science ever be able to tell us which one is the right theories for the early universe? I'm not so sure. I'm pretty sure that we'll be able to improve over the theories that we currently use. They have other shortcomings than the Big Bang, so I'm pretty sure we'll be able to come up with better models than this. But will we ever be able to figure out how the universe began? I'm very skeptic because of this issue that there's just no justification in science to attach a more difficult story before a simple one. If the early universe was very simple, then you can add all more difficult explanations before this, and we would never be able to figure out which one is the right one. So did the universe begin? We don't know, and we may not never know.
For more debates, talks and interviews, subscribe today to the Institute of Art and Ideas at IAI TV.